Hi, this is Miss Carly, and in this flip video we're going to look at two theorems. The first theorem is called the rational root theorem. Now, some polynomials are a little bit harder to factor than others, and sometimes the easiest way to find the factors is not always the graph. The rational root theorem, it basically tells us all the possibilities that our roots could be. It doesn't tell us exactly what they are for a fact, but it gives us an idea of what they could be. The rational roots come from the factors. So you can kind of use this with synthetic division to find all of the roots. It's just another way of finding the roots of polynomials, basically. So some of these are rational numbers and some of them are not. Rational numbers, if you can think about them coming from the factors, we have never factored polynomials where we have square root symbols. If you take the square root of something that's not a perfect square, that number is irrational. So that does not fall under this category. Rational numbers are whole numbers or fractions. Anything that you can rewrite like a fraction, and your decimal, you're allowed to get decimals, but they're usually not long, crazy, like irrational numbers. They're usually repeating or they have some kind of pattern. So this is a rational number. Now even though this is a radical, the square root of 4 is 2. And 2 is a rational number. 7 over 5, rational. Square root of 2, not rational. 2 is not a perfect square. So I have here a polynomial because I think the easiest way to go through this is just with an example. Be careful because the terms are not always going to be in order. You want to rearrange them so that the degree goes from the highest exponent to the lowest exponent. Now you have to pretty much have a constant here unless your rational root is just going to be 0. And basically all we're going to focus on is the very first coefficient and our constant, the number that has no variable attached to it. And all we're going to do is list the factors. Now, it's always positive and negative, whatever your factors are, because basically if I want to figure out what times what will give me 6, well, I could either do positive 1 and positive 6 or negative 1 and negative 6. So both of those are true. Instead of writing them separate, it's easier just to put the little plus minus sign. So all the factors of 6 are 1, 6, 2, and 3. We're going to call all of those category A. All right, come over to my last number, the one without a variable, my constant. I'm going to do the same thing, just list the factors. Still, always put the plus and negative for the same reason. 1, 10, 2, and 5. So I'm going to call those category B. If you wanted to figure out what could possibly be a root to this original or a 0 to this original polynomial, you can literally pick any number from the B category with any number from the A category. And if you write them, B over A, that could be a root. So I'm not going to do all of them because there's a whole bunch. But I could basically take positive 10 over negative 1. That could be a root. So basically that would be negative 10. Right? I can take negative 2 from the B category with negative 3 from the A category. That would simplify to just positive 2 over 3, but that could be a possible root. I'll do one more. You can take 5 from this category with 6 from this category, and that could be a root. All right, now if these are the roots, remember how we went basically from factored form? You would kind of like bottoms up to figure out, like if this was your root, then you would rewrite that factor as 6x plus 5. All right, so all these things are going to start kind of tying together. Same thing. If this was your root, you could rewrite that as 3x plus 2. But actually, you would want to change the signs because remember, your roots and your factors are always the opposite signs. All right, so there's your rational root theorem. All you do is factor the first number, factor the last number, and when you pair them up, it's always B over A. Any of those could possibly be roots. All right, the next theorem is called the remainder theorem. Now, we've been doing synthetic division with numbers that are roots. They go in perfectly. When you get back from break, we're going to start seeing some remainders in our answers when we do synthetic division. So the remainder theorem, it basically is just a way for us to rewrite our answers and try to figure out what the original polynomial was, like before you did any division. So if you do some polynomial divided by the factor. So in synthetic division, if it looks like x minus 2, we would just do 2. Same idea. Like whatever's here, the a, would go on the outside of your synthetic division box. All right, that's going to give us some answer. It's going to give us some new polynomial. It's always going to be 1 degree less than I started with, but there could possibly be a remainder now. So if you want to go back and figure out what the original polynomial was, it's basically just saying that you're going to take whatever you got in your answer, like whatever was on the bottom of your synthetic division, times whatever you had on the outside, and then you just add the remainder. It's basically just saying that these two, when you multiply them together and add r, it's supposed to give you back your original polynomial. All right, so I have an example here, and I didn't work out the synthetic division because we've been doing that a lot in class, but I want to take x to the third minus 7x minus 6 and divide it by x minus 4. So the positive 4 goes on the outside. It's basically the same thing as like your root. And when I get synthetic division, my last number is not 0, which means that 4 is not a root. I have a remainder of 30. So this is my polynomial that I got. This is like your q of x in the formula that was on the other slide. But my remainder is equal to 30. This is your r. All right, now technically that 30 is out of how many I was trying to divide by. So if you want to figure out what your original was, here's my new polynomial that I got. I would have to multiply that by the x minus 4, because that's what I divided by, but then you'd have to add your remainder. Now technically your remainder is not 30. It's 30 out of the x minus 4 that you were trying to divide it by. So the way that you have to write your remainder, if your goal is to rewrite what the polynomial was, you just take whatever number is in the circle. If it's 0, you don't have to worry about it. That means that this was a root. But if it's not 0, it's going to be some other number. You have to put that number as the numerator and then divide it by whatever you were dividing by in the problem. All right, so it's not really that tricky. You just have to remember to rewrite that like a fraction. All right, so technically if I do this, this was my answer that I got through synthetic division, times what I was dividing by, plus my remainder. All of this down here, if I were to work it out, is supposed to equal x to the third power minus 7x minus 6. Now, the reason they might need for you to know this is I might give you bits and pieces of these pieces of information and ask you to try to tell me what the original equation could have possibly been. All right, so it's just another way of you using some synthetic division and taking some of these multiplication rules that go with polynomials.